For most of this class, we've talked about computer algorithms where there's a right answer or a wrong answer. If you're predicting a word, labeling sentiment, predicting parse tree, or answering a question, there's one or a handful of right answers. Either you get it right or you don't. But today we're talking about something different. Not whether a computer gets the right answer or not, but whether the computer can explain its answer to a human user. As we'll talk about, the definition of interpretability is squishy. But let's use this definition from Hema Lakkaraju as a place to start. A computer's ability to explain or present in understandable terms to a human. Now, sometimes you don't need interpretability. If the stakes are low or the accuracy of the computer is nearly perfect, it doesn't need to explain itself. Netflix telling you what to watch next doesn't really need an explanation. Who cares if you don't like the Squid Game? Likewise, with zip code recognition, the accuracy is already superhuman. And if you're playing a game like Half-Life Alyx, you don't expect an explanation or predictability from the enemies in that game. But sometimes you do want accountability. As AI, whatever that means in popular culture, becomes more prevalent, we're seeing computers make decisions about who should be imprisoned or not, who should get medical treatment, or who should get a loan. If you were on the receiving end of such a decision and you didn't like what the computer thought, you'd rightly expect an explanation. Why am I being kept in jail? Why can't I get this medicine? Why can't I buy a house? So you need to measure interpretability, but the definition of interpretability that we're using here has these pesky humans in the definition. So how could you actually measure interpretability to know whether the explanations are good or not? This figure from Doshi, Velez, and Kim lays out a hierarchy for measuring interpretability. As you go up, the evaluations get super specific and expensive. Let's go through some examples for a particular kind of model, topic models, and how you might evaluate interpretability along this hierarchy. Brief refresher on topic models. A topic model takes a large collection of documents as input and spits out a summary or a list of words, a topic if you will, that summarizes the themes of a collection. For example, if you take New York Times as input, you get entertainment, arts, and business as three of your topics. Link to a fuller description of topic models in the description if you're interested. The great thing about topic models is that they're an unsupervised algorithm. There's no right answer. There are exponentially many ways to cluster a document collection. And from a theoretical perspective, evaluating clustering itself is theoretically very difficult. And if you look at any topic modeling paper, the goal is to create a useful tool for humans. So we need to measure interpretability itself. Slight digression, John Kleinberg actually proved that for 3 reasonable things that you'd want out of clustering algorithm, it's impossible to satisfy all 3. So again, the human needs to be the judge of what a good clustering or a good topic model is. So let's go through the hierarchy of interpretability evaluations. And as we go through them, you'll notice that out of some combination of familiarity, vanity, and laziness, I'm going to be using our own evaluations that we introduced for topic model interpretability. Let's start at the top. The most expensive evaluation requires real humans doing a real task. So what could you use topic models for? Let's say that you have a big pile of documents and you need to sort that into piles. You're organizing a conference and you need to sort the submissions into tracks where they'll be reviewed and eventually presented. You're a journalist, and you need to sort all the emails of a corrupt politician into themes. You're a lawyer, sifting through a company's documents through the discovery process, and you need to find out what the company was doing. You're a poor intern at the FCC after Colbert asked everybody to submit their comments on net neutrality regulations. Or finally, you're a political scientist looking at a decade of legislation and you need to categorize the bills into what they're talking about. And that's the real world application that we investigated here in this paper, which we called Alto. So to do that, we put a user in front of an interface that shows people different models, asks them to form piles of documents, i.e. create labels for each of the documents. And then we compare those piles into a reference set of piles where annotators essentially had infinite time to argue about what labels a document should get. The exact models, explanations, and metrics aren't important for this high-level discussion of interpretability here, but it gives you a sense of the trade-offs. First, take a look at the x-axis here. 40 minutes for a single evaluation? That ain't cheap. Also, something that's good at 1 minute might not be good at 40 minutes. A superficial first glance might be good, but it doesn't have the depth to remain useful for long. In other words, these experiments are dependent on all sorts of contextual factors. Who are the users? How much training do they have? How long do they have to do the task? If you care about this exact task, these results might indeed be useful for you, but otherwise, the results can suggest something to try. But you'll have to run another expensive experiment to know for sure. Let's move to the middle of the hierarchy. Instead of a complicated task that almost takes an hour, let's have humans look at a topic that comes out of a topic model for a couple of seconds. We've inserted something we call an intruder word into each of these topics. And if the user can find the intruder word that doesn't belong, then we hypothesize that the underlying topic, before the intruder word was added, made sense. If they just randomly click on any of these words, the topic must not have been very good in the first place. And from this, you can figure out which of the individual topics are good or bad. And averaging over an individual run of a model, you could then figure out which of the models, a collection of topics, are good or bad. But again, humans are in the loop. These humans can be very cheap, low latency crowd workers. But maybe you want something even faster still? So you'll notice that this paper here is called Reading Tea Leaves. So Lau et al. Came up with machine reading tea leaves techniques, which shows that if you look at how often words appear together in a large reference corpus, a metric called normalized pointwise mutual information, you get a pretty good correlation with the metric introduced in the previous approach from our group. And this is the cheap, fast, computerized bottom of the interpretability hierarchy evaluation. So if this works well, can we just forget about humans? No. And here I'll put myself back in the narrative again. While these automatic metrics show the same general trends as human metrics, they can impart too much certainty to the conclusions that you draw if you use them. While these functionally grounded evaluations are better than nothing, they need to be constantly and consistently validated against human interpretability experiments. If you want more of the story for topic models, you can check out my most popular video of 2021, which was the presentation of this NeurIPS paper, link in the description. So before we dwelled on how problematic the word human was, let's dwell on another word now, understandable. In a great paper, Zach Lipton trenchantly points out that this could really mean any one of a number of things that all impose a different meta-objective that makes the standard optimizations that we do in machine learning land more complicated, because it replaces the traditional objective that you optimize with SGD, say. So what could understandable mean? Let's go through some of the options discussed in this paper. It could mean that the user trusts the output of the system, but just because the answer is one that I want to hear, and the answer that I believe, doesn't mean that it's the right answer from either an objective perspective or from a societal perspective. More on that in a second. Think about some of the high-stakes examples we talked about from before, giving people medicine or approving a loan. In an interpretable model, you should be able to understand whether a potential client is more likely to default on a loan because they come from a particular zip code or because they have a negative checking account balance. In the literature, this is called causality. You might want to understand why something happened, not just that they're correlated. You also want models to be robust and transferable, even as circumstances change. For example, in this paper from Caruana et al., their explanation learned that asthma patients have a lower risk than other patients from pneumonia. Counterintuitive, right? But that's because when someone with asthma presents with pneumonia, it's an all-hands-on-deck moment. That patient gets lots of attention to prevent bad things from happening. But if you had just looked at the coefficients in the model, in a counterfactual world where asthma patients weren't prioritized, you'd end up making the wrong decisions about whether they were high risk or not. In that case, the model doesn't transfer to a new domain. Or you might just care about how much the user learns. In a future video, we'll talk about how we measured informativeness for a question-answering application-grounded setting. And finally, you might care about the societal impact of the computer-human system that's using the predictions and interpretations. This will be the subject of a future video in its entirety. But hopefully, this should give you a sense of the different aspects of interpretability, why we care about it, and the complexities of evaluating interpretability. Stay tuned for more. This is just a single lecture from a course. YouTube likes to show you these videos out of order, but if you go to the course webpage linked below, you can see the lectures in the right order, and you can get resources like homeworks or suggested reading. You can also visit quanta.org if you want to learn about our systems for creating computers that can answer questions, where Quanta stands for question answering is not a trivial activity. If you want to help the channel, provide a big gradient to the algorithm by liking and subscribing.